co-editors-in-chief. The other one is Professor Wenping Hu from Tianjin University. Today, Professor Richard Tilley is a speaker. Before his talk, let me briefly introduce him. Professor Richard Tilley is a director of Electron Microscope Unit and a professor in the School of Chemistry at the University of New South Wales in Australia. He graduated with a Master of Chemistry from Oxford University and then completed his PhD at the University of Cambridge. He was a postdoc at the Toshiba Basic R&D Center, Tokyo. He leads a research team focusing on the solution synthesis of nanostructures for catalyst and biological imaging. Today, he is going to talk about solution synthesis of branched nanoparticle catalysts. Let's welcome Richard to give a talk. Richard, please.
Thank you very much for the kind introduction. For the invitation. I'm really delighted to talk to you today. So I'll be talking about some of the research work that we've been doing making branched and faceted nanoparticle catalysts. And I'm particularly pleased to be invited. I know the title of the journal is Smart Matter. And actually, the group we have in UNSW in Sydney. So I actually have a joint research group with Professor Justin Gooding, and the title of our group is Smart Materials and Surfaces. So we do a lot of work trying to make smart materials. So it's fantastic to work with Justin. Justin is a very eminent professor. He's the editor-in-chief for ACS Sensors, and he's a fantastic chemist, particularly on terms of surface chemistry, electrochemistry, and also he does a lot of work making smart materials for sensors and wearable sensors. So it's great to work with him. And this is, just so I show everybody at the beginning, this is actually a picture of our research team. So as you can see, it's a very cosmopolitan, lots of different faces and different nationalities. So Sydney is a really great city and a fun city to live in, and we have lots of students from different parts of the world. So today I'll be talking about the work that's been particularly done by Agus, who's this student here, and Lucy, and also Ali as well. So they're the three students that have done most of the work that I'm going to be talking about today. So for my own particular research focus, what we look at is basically how to make nanoparticles with solution synthesis with really a very precise control of the particles that we make. So today I'll be talking about these types of catalytic nanoparticles where we have a branch structure, but also with the branch structure, we have some particular surface faceting. So you're really trying to control this shape. We also do a lot of work making MRI and magnetic particle imaging tracers. And, you know, this type of application, you really need very fine control of the nanoparticle size to get the properties you're after. We've done a lot of work making bimetallic catalysts, again, where you're trying to get very fine control of the particles you make to really tune the catalytic properties. And we've also done work, again, a lot of work making low toxicity quantum dots of silicon. And again, you really need to control the size to get the optical properties that you're after. But today I'll talk about branch particles for catalysis, and we've really had a lot of fun making these particles. They're very beautiful particles, and also they're very good and effective catalysts. So this is first of all looking at ruthenium nanoparticle catalysts for the oxygen evolution reaction. So when we think about the oxygen evolution reaction, it's one of the electrodes for the water splitting electrolyzer. So this is the type of fuel cell that you would use. I live in Australia, so if you can imagine if we put lots of solar cells across the desert and out back in Australia, they could generate a lot of electricity, but you need a way to store this energy so you can use it later at a time and a place that you really, really want to use it. So this is a fuel cell. While you're putting in electrons, you're putting in electrons as the energy, and essentially you're generating hydrogen as the fuel that you can store and use later. And for the anode reaction, you have the oxygen evolution reaction where you're splitting your water and you're making your oxygen. So we'll talk a little bit about hydrogen evolution later in the last example that I'll give. Okay, so as I said, this is work that was done by Lucy and Agus. So this is Lucy and Agus up here. And particularly what we were looking at for these kind of particles was really to try and find better and more effective catalysts. So actually, ruthenium is a really, really active catalyst. In fact, it's the most active catalyst for the oxygen evolution reaction. So you can see up here that you can get some really, really active catalysts for ruthenium for OER. But the problem is that they really have almost no stability. So on this axis here, we have number of cycles, and this is actually a log scale. So when you're cycling these ruthenium nanoparticles after even just 1 or 2 cycles, essentially the ruthenium catalysts are just dissolving up into the acid electrolyte. And then your other kind of option is that you can use oxide catalysts. And the oxide catalysts are great. They're very, very stable, but they don't have anywhere near the activity that the ruthenium metal, oxidized ruthenium metal catalysts have. So we felt that there was a lot of empty space in this area here. So we wanted to try and see if we could make some catalysts that could start filling this empty space by being both active and hopefully have some stability for ruthenium metal. So we kind of drew our inspiration from quite a bit of the old thin film research on electrode catalysts. So there was some nice work done just on thin film electrodes with ruthenium about 20 years ago that really showed that if you could have nanoparticles of ruthenium which had low index facets for the electrode material, then for thin films, low index facet ruthenium was actually more stable. So when we say low index facets, we're really talking about facets that have Miller indices of 0s and 1s. So these are our low index facets. So these are the facets that we're chasing. And as I say, the problem with ruthenium is it does tend to be unstable when it's oxidized and catalyzing for the oxygen evolution reaction. So we have to oxidize ruthenium up. And when it gets to these high oxidation states, it's very, very easy for it just to dissolve up, as I said, and go into the acid electrolyte. So in terms of making ruthenium nanoparticles, which have these low index facets, which we hoped would be stable for OER, synthetically, it's actually quite a challenge, which is great, because the types of ruthenium nanoparticles that really people have managed to make before, these are just a couple of examples from the literature. But as you see, you don't really have much faceting, and you certainly don't have a lot of kind of stable low index facets. So we set about designing synthetic methods and synthetic approaches where we could make some branch particles, because they should have a high surface area, and also branch particles with these low index facets. And these are the particles that we ended up making. So if you have a look, this is a TEM image of the particles. So you can see that for each of the particles, we have a dark core. So each of the particles actually has a gold core in the center. And then off the gold core, we have these kind of wedge-shaped ruthenium arms that grow off this central gold core. So we've got all these wedge-shaped arms growing off this dark center. So actually we end up with particles that look a little bit like this. So you gold core and then these faceted arms. And then we can do our high resolution electron microscopy of these particles. And we can look at the high resolution image. So we have all this beautiful atomic resolution where we can see the atoms. And then we can index these surface facets to identify them and see what we have. And as you can see, we were very pleased that when we did this synthesis, we actually ended up with ruthenium branch nanoparticles with the low index facets that we're after. So these facets that have ones and zeros in them. So that was great. So we made these particles, and you can always have your kind of your hypothesis and your idea that hopefully that your design is going to actually give a good catalyst. So we're very pleased that when we actually looked at the catalytic properties of these branch ruthenium particles, they were actually very, very nice catalysts. So if you have a look here, we can see that we have high activity because, as you would expect, we've got ruthenium nanoparticles, so we would expect to have the high activity. And if we look, say, in terms of how much the activity decreases after 200 cycles, you can see that after 200 cycles, even after 200 cycles, we still have very good activity. So even after 200 cycles, we actually still have about 90% of the maximum activity that we achieved. So for us, this was a tremendous result because, as I said, for all the other examples of ruthenium nanoparticles for OER, they would always just dissolve up into the electrolyte after about 5 cycles. They're all completely gone. So this was the first time there was really an illustration that you could make ruthenium metal-based nanoparticles that could have some stability for oxygen evolution reaction. So if we want to think about a little bit more, and this is some of Agus's work that was published in Small. So if we want to think a little bit more about how we can make these stable, active catalysts with these low index facets with ruthenium, then essentially we need to have a think about what the ruthenium is doing during OER. So when we oxidize up the ruthenium to these higher oxidation states on the surface of our catalyst, essentially the ruthenium, these oxidized ruthenium atoms have two choices. They can either stay on the surface and sit on the surface and then catalyze your OER process, or they can dissolve up into the solution. So if we have a look at the Faradaic efficiency of the oxidized ruthenium particles, when we have these low index facets, they actually have a very good Faradaic efficiency. So that means that during the electrocatalysis, the oxidized ruthenium is doing a lot of catalysis rather than dissolving up into the solution. And if we have polycrystalline ruthenium catalysts, essentially we have very low Faradaic efficiency because all of the energy that we're putting in is oxidizing up our ruthenium, and then that's immediately just dissolving into the electrolyte. So we don't have very good Faradaic efficiency before at all. And if we want to think about why, well, it's quite understandable. If we have these low index facets, we have our ruthenium atoms on these low index facets. They have a high coordination number. So when they're oxidized up, they're being held on that facet by maybe 6 or 7 or 8 other ruthenium atoms are bound to it and holding on to it and keeping it attached to the surface. Whereas if we have our polycrystalline ruthenium, when they're oxidized up, they may be bonded only to 2 or 3 or 4 other ruthenium atoms, and then it's very, very easy for them to just dissolve and go up into the electrolyte. So this is really an indication of why these low index facets might be really what we're after in terms of the catalytic surfaces that we want to achieve. And the nice thing about if we then go back and have a look at this kind of plots that we can do in terms of looking at how active and stable different catalysts are. So in terms of where these branch ruthenium systems actually sit on this plot, we are actually starting to fill some of this empty space, which is nice. So as I said, we have our good activity because we've got a oxidized ruthenium catalyst, but actually when we cycle, say even up to 1,000 cycles, we're still getting good retention of the initial activity. So, as I said, they're really nice catalysts, these branch ruthenium structures. So as a synthetic chemist, the question is, how do you make them? So how do we go about making these kind of branch structures with these low index facets? So we've been doing quite a lot of work on this over the years to think about growth mechanisms and mechanisms for making branch structures. And we now have mechanisms for really making this type of particle that we've been thinking about a lot. So the first example that we came across making branch structures was quite a few years ago. So this is over 10 years ago now. And this was making some branched palladium structures. And the way we could make these branched palladium structures was essentially by controlling the growth kinetics of the system. And in this kind of reaction with these palladium structures, the reaction was essentially uncontrolled, and it was going quicker and quicker and quicker and quicker until at the end of the reaction, the decomposition of the palladium precursor was going really, really super fast. So we were ending up with a lot of dendritic growth and dendritic structures at the end. So although this is a way to make branch particles and branch structures, because it is so uncontrolled, what you do actually end up with at the end is these kind of structures that don't really have surface facets and don't really have particularly the low index surface facets that we're really after for a lot of catalytic reactions. So the way we hit upon actually making branch structures which do have some faceting and do have a degree of control was from a student, Alec Legros. And Alec was playing around making nickel nanoparticles, and he ended up making these very nice branch nickel structures. So when we want to think about how we can make these branch structures, then we really have to look at the different crystal phases that we're forming with the nickel. So at the beginning of the reaction, when we look at the nuclei, we can look at the electron diffraction pattern, and we can see that we're forming predominantly or exclusively face-centered cubic nickel. So this is our cubic FCC nickel. And then as the branches are growing of our nickel cores, as the branches start to grow, we could look at the electron diffraction pattern and see how that changed. And we could see that we were starting to get some hexagonal close-packed structured nickel into the reaction as these particles were growing. And then as the arms grow longer and longer and longer, we're actually ending up with more and more hexagonal close-packed nickel in our sample, in our structures. And as you can see, these structures are more the structures that we're after. So we have a nice core there, but we're actually ending up with these very straight edges and straight tops, which indicates we are getting towards the kind of the LowIndex facets that we're really after. So this was all with pure nickel in a one-pot synthesis. So you're just putting in your nickel precursor and doing your reaction and seeing what you'll get. But this really gave us a clue for the mechanism that we want to chase. And this mechanism really relies on having cubic close-packed and hexagonal close-packed structures. So if you remember from your undergraduate days, you can think about your close-packed structures. You've got two close-packed structures. You have your central atom, and then you've got your other 6 atoms packing around to give you your maximum coordination number, your highest possible packing density. And we can have cubic close-packed, so we can have our layers of atoms being in one layer, then a 2-layer, so A, B, C stacking. So all of these layers are in different positions. Then going back to A again, which is directly above your first layer, so A, B, C stacking for your cubic close-packed. And for your hexagonal close-packed, you've got your A, B stacking, so this layer of atoms is directly above the first one. And when you have these hexagonal close-packed structures, you have some natural anisotropy. Your A and B axes tend to be shorter than your C axis. So in that case, you can get rod-like or branch shapes forming if you form with these hexagonal close-packed structures. So this kind of mechanism was identified by Liberato Manna when he was working with Paul Alvasatos. And this was how they were making these beautiful cadmium telluride, cadmium selenide tetrapods. So you have a cubic crystal structure core, and then to get your arms grown, you have a hexagonal close-packed structure to get that arm formation. So this is exactly what we were getting with our nickel system. We would have a nucleation of a cubic structured, an FCC structured, cubic close-packed structured, face-centered cubic core, and then off that core at very, very precise crystallographic angles, because you're just changing your stacking from ABC, ABC for your cubic structure, switching it to from ABC, ABC into AB, AB, AB for your hexagonal structure. So you're going off very precise crystallographic faces. So you get very precise crystallographic angles in the particles you're making with your HCP structured arms. So this was great. And this was the first example really with metals where you could use this kind of this polymorphism structure using 2 different crystal structures to make a branch metal structure. So that was really good. But the problem is, as you can imagine, you're just putting your nickel and precursor into one pot and decomposing it. It's quite hard to really control if you're going to get face-centered cubic nickel, hexagonal close-packed nickel, and also to how to control that switch from one to the other. So we wanted to use this mechanism a little bit more deliberately. So this is how we thought about starting to make these branched ruthenium structures. And essentially how we do it is we make some preformed face-centered cubic structure seeds. So typically for a lot of the reactions that we do, gold forms face-centered cubic crystal structure. So we often use gold nanoparticle seeds because gold always has a clean surface as well. It doesn't tend to oxidize. And then off that FCC structured seed, we want to grow a hexagonal close-packed structured metal to get our branches. So ruthenium is a hexagonal close-packed structure. So when we're doing this kind of reaction, we really need to control the concentration of the second metal during the reaction. So in this case, if we're growing ruthenium branches, we really need to control the amount of ruthenium monomers or ruthenium zero valent atoms ruthenium metal atoms in our solution. So the important thing is that you always want to really have a low concentration of these ruthenium zero valent atoms. So if you have your gold seeds in the solution, and then you have your a low concentration of these zero valent ruthenium atoms, the only choice they have as they're moving around in solution is to stick onto the gold. You can then form your core shell structures and start to grow your arms. If you have too high a concentration of the ruthenium zero valent atoms, you'll cross your critical concentration. The ruthenium atoms will start to bump into each other. You'll start getting nucleation, and then instead of getting your core shell structures and your branch structures, you'll end up just with a mixture of gold nuclei seeds and ruthenium nanoparticles. So when we do these reactions, we really have to do them in mild conditions to really have this very slow generation of ruthenium. So when we do one-pot syntheses, they can be very, very effective, or, hot injection synthesis of nanoparticles, heating up synthesis of nanoparticles. They're excellent methods. And they tend to make nanoparticles sometimes in the space of just 1 minute. But when we're doing our kind of coating reactions, we really take a lot of time. So we're very relaxed about it all. And really, we let the reaction really react for a long, long time, particularly compared to just these few minutes. So typically when we're doing these reactions, we kind of leave them cooking for hours or sometimes days. So it really does give you an indication of how slowly we're decomposing our second metal precursor. So what we do to make these branch ruthenium particles, we make up a batch of gold seeds. We put them into a Fisher Porter bottle. So we have a solution of our gold nanoparticles and our ruthenium precursor. We put them into a Fisher Porter bottle. So a Fisher Porter bottle is just one of these glass bottles. And then we fill the bottle full of 1 atmosphere of hydrogen gas. So the hydrogen gas is a very, very mild reducing agent. And it's the hydrogen gas that will reduce your metal ions down, say, from ruthenium-3 to ruthenium-0. But it is a very mild reducing agent. And this is the key or the trick to give us this very slow trickle of our ruthenium metal atoms. And then they'll nucleate and grow onto our gold seeds that we put into our solution. So as I said, we tend to be quite relaxed about how we're doing our chemistry over here in Sydney. Okay, and then we can end up with these kind of beautiful structures. And as I said, you have these gold cores, and then you get your ruthenium arms, your ruthenium branches growing off the gold cores. And the other important thing that we do in the solution is put in some dodecylamine. So dodecylamine is a surfactant that binds very strongly onto ruthenium. And it's good because it binds strongly, so it stabilizes these low-index facets we're after. So that's our surfactant that we put on that'll really bind and stick to these low-index facets and stabilize them. And then we can take our our Fourier transform of the high-resolution image. We can index our Fourier transform and then start to assign which surface facets we have on our particles. So, again, for those of us who really enjoy these mechanisms and really like these mechanisms, we looked at two different seeds to see 2 different types of particles, 2 different approaches. So if we use gold metal seeds, essentially you don't have a good lattice matching between gold and ruthenium. There's a big lattice mismatch. So it means that the ruthenium atoms can't epitaxially grow and stack onto your gold core. So if we have a look at the particles we make, rather than growing off very precise crystallographic faces, we actually grow off in very random orientations. And if we have a look at the kind of how the growth occurs, then first of all, we get a kind of a ruthenium shell growing on our gold core. And actually, it's ruthenium growing off ruthenium to end up with these particles. And with the electron microscope, we can see there's lots of stacking faults and things because of this lattice matching or lattice mismatching. So the second type of particle that we looked at, and this again was deliberate, was palladium has a very good lattice matching with ruthenium. So we thought in this case, if we use palladium seeds, we should have the good lattice matching and we should start to see this epitaxial growth and this orientation. And that's exactly what we did see. So this is another paper from Lucy. So in this case, we have palladium as our seed. We have very good matching of the spacing of the palladium atoms with our ruthenium atoms. And so we do get this epitaxial growth. And then we get these very precise angles. So 180 degrees, 120 degrees, 109 degrees when we're growing off these specific facets. And if we have a look at the high resolution TEM image and we have a look at the interface between our palladium core and our ruthenium branch, we can see that we have our ABC cubic packing from our palladium, and then we're switching when we get into our ruthenium to our HCP AB packing as we have a look at that interface. Okay. So in terms of kind of thinking next, so we know that we got kind of a nice mechanism for making some branch structures. So we were very interested to see, as I said, with the nickel system, it was quite hard to control. So we wanted to go back to that one and see if we could make some branch nickel structures and really get some good control of branch nickel. So this project is looking at having gold seeds again as our face-centered cubic seed, and then having nickel as a hexagonal close-packed structure arm coming off our gold seed. And this is in collaboration with Wolfgang Schumann from Bochum, and he does a lot of the catalysis with us. So this was looking at nickel for biomass oxidation. So as I said, with the pure nickel, we could get branch structures, but we didn't really get the control that we were after. So to make these branch nickel structures, and actually Agus visited one of my former students and started doing some of these experiments. So John Watt, who actually did the palladium work that I spoke about earlier, he's now got a position as a research scientist at Los Alamos in the States. So Agus went across and visited him. So to make these branch nickel structures that we were interested in, you just put in your preformed gold seed, and then you can decompose your nickel 2+ onto your gold seeds, and then end up with these branch structures. And that's exactly what Agus managed to do. So if you have a look at this electron microscope image here, this is our branch nickel structures. And this is one of my favorite TEM images of all time, because normally when you're taking a TEM image, it's a two-dimensional image, a 2D image of three-dimensional structures. But somehow I feel with this image, somehow the 3D structure of the particles does somehow come across. And if we have a look at our dark field image and our EDS mapping, we can see that we can pick out the gold seeds, the gold cores, and then we're getting these nice nickel branches growing off our gold cores. And again, you can see we're getting the kind of the sharp facets that we're after, these low index facets that we're after for our catalysis. And this is a video of some tomography. So this is TEM tomography, where you tilt the branch particle in the TEM, and then you can get a rendering and a structure of what the particle actually looks like in 3 dimensions. So this is one of the branch nickel structures that Agus made. And again, we can do our high-resolution electron microscopy. As I said, we have these nice, sharp, straight edges, which is what we're after, and our sharp, straight edges at the end of the particle. And we can do our indexing of our high-resolution electron microscope image. And again, this is a nice picture in terms of seeing the A-B stacking that you get from a HCP structure. You can kind of see how the diamonds look going across, and then we can index and see that we get our low index facets again from our structure. And with this, with these reactions, we could Agus could really get really great control, particularly of the length of the arms. So if you just change the concentration of how much gold seed he put into the reaction compared to how much nickel precursor, if he had a lot more nickel precursor compared to the amount of gold seed, he was getting longer and longer and longer arms. And this was interesting or interesting from a catalytic perspective, because this surface facet along the sides, we did some DFT calculations with one of my colleagues, Priyank, and his calculation showed that these facets along the side should be more active in terms of our HMF oxidation, our biomass oxidation, than these end surface facets. So we felt that if we had longer arms with more of these exposed facets on the side, then we should have better catalysts. And that was indeed the case. So I think in terms of how we can go about designing or making better catalytic particles, one option is to take expensive metals like ruthenium and see if we can make them more active or more stable. If we're looking at trying to make catalysts from more earth-abundant, cheaper metals, such as nickel, we can try and make them more active, but often that's quite a difficult challenge. One other option is that we try and look at using them as catalysts for reactions which are more easy to catalyze or require less energy to catalyze. So we looked at the branch nickel particles for oxidation of biomass rather than as catalysts for the OER reaction. So when you're doing your biomass oxidation, you're taking your HMF and you're oxidizing it up and turning it into a more valuable product at the end of the catalytic reaction. So turning it into your FDCA. And as I said, actually the catalyst for the longer branched arms, they were the most effective catalysts, and actually they were 3 times more active than if we have spherical nickel nanoparticles. And in terms of if we compare how good a kind of catalyst they are for a harder reaction like OER, then they weren't great catalysts, but certainly oxidizing up the biomass are actually pretty efficient catalysts. And some of this catalysis studies was done in collaboration with Da Wei, who's another colleague from UNSW. Okay, so the last topic I wanted to talk about was, I guess, kind of the next step for us in terms of what we're thinking about in terms of what we want to do next. So we've got these methods for making branch particles, and the other side is, can we actually start using these branch particles as templates? Because when we do this coating reactions, they're very, very effective. So we feel that with these coating reactions, we can coat a lot of things, even things which are quite challenging. So this is looking at platinum nanoclusters, platinum islands on branch nickel particles. So this is now using our branch nickel particles actually as the seed. And this is some of the particles that we made. So you can see your branch nickel structure, and all of these red dots are basically the platinum islands decorating the surface of the branch nickel. And our motivation for this was the opposite reaction, the other reaction for the OER reaction. This is the hydrogen evolution reaction. And nickel platinum structures are really, really good catalysts for hydrogen evolution. So this is the reaction where you're taking water and essentially you're breaking that hydrogen oxygen bond, and then you're basically forming your hydrogen gas at the end of that. So nickel platinum together is a very effective catalyst, because when you have your nickel next to your platinum, the nickel itself has a high affinity for your OH. So the OH part tends to bind to the nickel, and that enables you to break this bond here and get the hydrogen absorbing onto your platinum a lot more easily and a lot more readily. So what we can have then, once we've broken this bond here, we can have two hydrogens on two platinum atoms, then they can join together and form our hydrogen gas. So if we want to think about catalyst design, to make good catalysts, what we want to think about is really, first of all, maximizing the number of our platinum nickel interfaces on our catalyst. So we want to have a lot of these platinum nickel interfaces to make a good catalyst. So that means we want small islands where there's a lot of those interfaces around the islands. And then the next kind of trick that we can do is basically think about introducing some strain into the system, and if there's some strain. So a lot of people have been thinking about how you can use strain to improve the catalytic properties of nanoparticles. It's really a very well established and well understood field. So actually there's a really large lattice mismatch. So the crystal lattice, the spacing between the atoms and platinum and nickel is actually a 10% mismatch, which is really large. And normally if you want to grow one metal on another, normally you need to have a lattice mismatch of only about 5% or lower to get your atoms to line up and join onto each other. So we love this because it's kind of synthetically challenged things. So nobody had really ever grown platinum or nickel before for nanoparticles. So we thought that was a great challenge. But also it should make great catalysts because of this mismatch. You should have a lot of strain. So this is our nickel and this is our platinum. And then as the platinum's joining on the nickel, it'll be very strained and very compressed together, a lot closer together than it would normally like. And this is important because one of the limits for the hydrogen evolution reaction is actually the hydrogen, when it's absorbed onto the platinum, tends to absorb a bit too strongly. It's stuck on too strongly. So if you can introduce this strain, it means that these can come off a lot more easily, and then you can actually form your hydrogen gas a lot more easily. So we want some strain in there to weaken this platinum hydrogen bond to again introduce increase the catalytic properties. So Ali was the student who did this work. So he put in his branch nickel structures into our Fisher Porter bottles. He put in some platinum precursor, decomposed the platinum precursor. And as you can see, he waited a couple of days and then he looked what it made, and he'd made these very small islands. This is a dark field image, so you can see the brighter platinum. It made these very small islands of platinum and decorated directly onto the surface of the nickel. So again, because this decomposition is so slow, you have these platinum atoms whizzing around in your solution, even though they don't really want to join onto nickel because of this last large lattice mismatch. They really have nowhere else to go. So they do start sticking onto the surface and forming islands. So if he waited a couple of days, he got about 2 nanometer islands, and if he waited a bit longer, 3 days, the islands could grow a bit larger as well. So in terms of kind of seeing if we do get the strain that we're after, this is a high resolution image. And hopefully you can see, but this is our nickel here. And if we say follow down one of these lines of atoms, you can follow down and see that it's kind of a straight line. But when we start getting to the platinum island here, you can start seeing that it kind of starts to bend and distort. And that's actually the strain that we're seeing visually with the TEM. So all this, we can do Fourier transforms of these images as well, and all this streaking is due to the strain of the islands. But it's lovely to do the TEM, but if you want to be a bit more, look at the entire sample, it's far better to do some synchrotron studies as well. So we did some scattering studies with a great collaborator, Bo. So he did some synchrotron studies for us, and he did some pair distribution function analysis, so he could calculate the average platinum bond distance, and he could calculate that we actually did have a lot of compressive strain. So actually for the small islands, as you would expect, the smaller the island, the more strain you have. So actually they had over 5% strain for the small islands. And then in terms of the catalytic properties, they turned out, the particles themselves turned out to be really good catalysts. So as I said, we've got these two strategies. We want small islands to maximize our number of interfaces between our platinum and nickel. And the smaller the islands, the greater the strain will be. And actually, if we have a look at the catalytic properties, the small islands are more active. Certainly than commercial platinum, and certainly more active than the 2.7 nanometer islands. So they're about 7.5 times, the small islands were about 7.5 times more active than commercial platinum. And in terms of mass activity, actually, this is a record for the mass activity for platinum. So because the platinum's all on the surface, it's all exposed, you can get very high mass activities. And because of the strain, you get good activity as well. So actually, these really do have very good mass activity in terms of platinum for HER. Okay, so I think I'm coming to the end now. So just to put a bit of context. So what we'll think about next is using these branch particles maybe as templates. And of course, there's lots of people doing beautiful work, particularly on manipulating stacking and all this ABC, AB stacking, and trying to get different structures or crystal structures than you would normally have. This is an example from Yunan Shah's group. So as we've seen in this talk, Ruthenium wants to form naturally a HCP structure. So they managed to get Ruthenium to form with a face-centered cubic crystal structure by using a cubic structure.
They have some general strategy to design some novel nanoparticles with high performance. He want to get some general strategy or some regulation or even guideline for the nanocatalysis. Yeah. Yeah.
Look, there's so many different approaches. So I think that really what we're after now in terms of state of the art, I think that particularly with the latest electron microscopes, it's changing so much. So state of the art and catalyst design, making a good catalyst 20 years ago would just be making, say, a monodispersed sample of particles all the same size. And maybe 15 years ago, it was making monodispersed particles that were all the same shape. So if you could make all cubes, you could understand the catalytic properties of, say, specific faces. And then now we're really looking at these bimetallic systems. So you want to not only control size, you want to control the shape and the facets, but also the metals. And of course, the cutting edge now is things like single atom catalysts as well. So where you're really getting atomic placing. So I think in terms of general strategies, I think it's there's just so much to explore that I kind of almost have a different approach, that almost anything you can make can be quite beautiful if you just look at it in the right way. And sometimes you just need a bit of luck in the lab, especially when you're a student. But just seeing those opportunities is the key point, I think.
Okay, thank you very much, Professor. The second question is about the stability of the nanoparticles. I want to ask, have you considered stability is good or not good? Just in your some examples. Yeah, the stability is very important for the catalyst. So I want to ask this question.
Absolutely. So I think that's another great question. So if we have a look at, say, our ruthenium catalysts, it's great. There's some stability, and certainly compared to ruthenium metal, where there's normally no stability at all, it's a big improvement. But still, after 1,000 cycles, we do see we're dropping in terms of stability. And if we really want to use these catalysts commercially, they have to be stable over tens of thousands of cycles. So we still have some way to improve, which is great. It gives us, again, an opportunity to go and try and think about how we can make them more stable and more better. So I think that the key for us, the next question for us anyway, is if we have these low index facets, what are the weak points? Where's the point in the particle which might be the point where we're starting to get the particles to degrade? So do we have particular points on corners or things that even though we have stable low index facets, there's particular points on the particle which might degrade? So I think that's a question that we want to try and answer and understand. And then if we can we might be able to protect those points and make even more stable catalysts and get to the stability that we would need for a more commercial fuel cell. So we're trying to think about if we can do some, say, in situ electron microscope studies where we can watch these particles actually degrade over time and see how they're degrading. But that's another step.
Okay, thank you, Professor. And the next question is about the solution method. all these actually the solution method is very simple and facile. Maybe there are not so many factors to affect the synthesis. But he want to ask, in your opinion, which is the most determinant factor to lead different structures in the solution method? Because in opinion,
again, that's another really great question. So the synthesis, in some ways, you can think is very complicated. In some ways, you can think is very simple. So particularly what we are focusing on is that for these type of reactions, for example, we know we want a cubic metal core, and we want a hexagonal close-packed metal for the arms. So we kind of understand that. The other important point is your choice of surfactant. So you want, if you after specific facets, you need to have one that's going to bind strongly to your metal. So that's important. So, we use dodecylamine for the ruthenium. For the nickel, we sometimes use top as a surfactant as well, because that'll bind strongly to your nickel. So you do need to kind of think of a few factors. And the other key point, as I said, is really for us anyway, these very, very slow times. So you can do these one-pot syntheses in kind of the space of a minute. But as I showed with our decorating, actually to just grow these very, very small platinum islands on our nickel, it actually took 2 days. So you could put your reaction on, stop it after a day, look in the microscope and think you haven't got anything. So you do need these very slow processes. The slower the better, really. If you're after a thermodynamic product, and if you're really after a coated product where you're getting the heterogeneous growth.
Okay, thank you, Professor. Another question about some details. And he said in your talk you provide several mental nanoparticles, such as PT, such as RU, such as gold and nickel. He want to, maybe he's not familiar with this field. He want to, how do you choose those metals? Yeah. Maybe he's not familiar with it. Why this is better than the other? So he want to know why. Yeah.
Why one is better than the others?
Yeah. Why do you? What's the guideline for you choosing the metal? Yeah.
The metal.
Yeah.
So it depends. So we choose the metals on the catalysis. Okay. So depending on what reaction we want to catalyze. So particularly, for example, for HER, for the hydrogen evolution reaction, then nickel platinum is excellent. So we deliberately tried to make platinum on top of nickel. We know that ruthenium is the most active metal for oxygen evolution reactions. So we targeted deliberately ruthenium. And then the other thing that we do deliberately is when we're doing these seeded reactions, we tend to prefer to use gold seeds, because the nice thing about gold is that it doesn't oxidize. So you always have a clean metal surface when you're growing the next metal on top. Whereas if you use something like silver, sometimes you can get a bit of an oxide layer, and then the next metal doesn't want to grow on top as much.
Okay.
So those are some of our
Okay,
thoughts.
thank you, Professor. And I also have one question, because I'm not familiar with your field, but I have a question. In your talk, you have displayed us several morphologies, some structures, beautiful structures for your nanoparticles. I want to ask if the structure or the different morphology can have very significant effect in the catalyst performance. Yeah.
Absolutely. Yeah, that's a really excellent question. So particularly in terms of the different surface facets, they really can control the catalytic properties, and that essentially is the morphology or the shape. So we do tend to target shapes that we think will have good catalytic properties. So the best example in this talk is these kind of nickel structures. So as we're growing longer arms, we were essentially changing the ratio of these side facets compared to how many nickel atoms are on the end facet. And actually, it's this side facet that's the more active. So this is the kind of shape that you're after with the longer arms rather than shorter arms for the better catalyst in this process.
Okay.
So yeah, the shape can really control the catalytic properties tremendously.
Okay, thank you, Professor. Yeah, Professor Hua Zhang, do you have some comments?
No, great talk. I think the time is quite limited.
Yeah. Okay, and if there were no question, and we want to thank Professor Taylor again. Thanks for giving us a wonderful talk about your research, especially so beautiful structures and very high performance in the catalyst. Yes, Professor, thanks again. And we also sincerely invite you to submit your work to our Smart Math journal.
Absolutely.
Thanks you very much, Professor. Thanks again.
You.
Yeah. See you.
Richard, thanks for your very nice talk.
Oh, thanks for that.
Yeah.
Thank you very much.
Yeah.
Thanks for the invitation.
Hope to see you face to face next time.
Absolutely.
Right.
Absolutely.
Okay. Bye-bye.
Yeah.
Bye.
Bye.